So good afternoon all and welcome to another session of structural analysis. I had two consecutive classes earlier, then that's why it was there. And by the way, please collect your writing tools because it was unplanned. However, I had to take this session, so we'll be carry on with calculating uh, little complex, little challenging numerical today, and we'll simplify the concepts of how to handle the non-uniform loading on the cantilever with UDL today. And that's how I will be taking one numerical which is simple in value, and then onwards we'll try to solve this combined effect of UDL and the moment again, right? So I'm going to give you a problem statement which you can start working on, and let's take it like this as an example. Okay. So you all will write down this in your notes with the values. Let's say, sorry, this is equidistant 2 meters, 2 meters, and again 2 meters. I hope it is visible to all of you. Like what is the load is, let's say 10 kilonewton per running meter, and we'll keep it as it is, like A, B, C, and D. Okay, friends. So let us learn how to handle this loading, which is non-uniform, as you can see, which is just in the middle of this beam. And let's try to start the analysis. Before that, let's write down EI as 10 into 10 to the power 13 Newton per mm square, right? And what we want today, we will explore the deflection at D, slope at D, then deflection at C, and also we'll try to cop up slope at C. Right? You can do other variations also here, but we'll try to finish it up as far as possible. And one important behavior I would like to discuss on this case of this beam, right? One important understanding will come out once you calculate values of theta d and theta c. When you calculate these two things together, you'll be able to understand one behavior, particular behavior of the cantilever, right? So we'll see it later on. So first come first serve, we'll go with deflection at point D. So who will guide me now? Uh, Today I would seek your guidance for solution. What should I do first? First of all, I give you the answer actually. As I said, it's little challenging to cop up the third session today, continuous third session. So you may find some problem with the voice also, but I will try to justify it as good as possible. Don't worry. So who will respond to the question? Like how should we start? Our target is deflection at point D. Who will tell me so that I can unmute him or her? How should I start? Anyone? Yes, Henry. Yes, Henry, tell us.
You apply a fictitious load P at point D.
Very good, excellent. That is what the answer I wanted. So now you guys are well tuned with this method. So thank you, Henry. We'll carry on as Henry has suggested us. We will put a point load because that is a rule of the energy principle number one. That where the point in which you want deflection, there has to be associated point load by default. And if it is not, as in this case, you have to apply it fictitiously, right? So let's apply it and let's go ahead. Let's use p force whose value is 0. Okay, and this is already the value of this UDL which already we have 10, right? So now we are ready to start with our table formation A, B, C and D. You can see there are three segments now. So first segment D to C, what is the origin? D is the origin. What is the length? 0 to 2 meters, right? You guys can do this along with me, and if you are comfortable, there's don't wait for me, you carry on with the calculation and keep me answering the questions. Right, let me take the calculator in hand. Today you may face some voice disturbance also. I had to keep my window open, which is at the office. Okay, so now we are ready to develop mx. So what would be the equation? Anyone? I'm waiting for the answer. Who will tell me the equation for mx for this portion? Darsha, tell us.
Sir, minus px.
All right. So it is, yes, quite obviously it is minus px, right? And then what next will be del mx upon del p, right? So it will be minus x. Okay. So till here, I think all of us are very much confident. So there is no need to go for the other opinion. So let's go for C to B. Second option, origin is C, length is 0 to 2 meters. You know the mx, like this force has to be considered in this portion. So it has to travel 2 meters ahead and x will be somewhere here. So we know that, sorry, first p will come here in the picture. So let's write down p 2 plus x. All right, and then you have a UDL, so 10 into x square by 2, and then you can have del mx upon del p, so it will be negative 2 plus x, like this. All right, so I hope it is okay and fine with all of you. So let's go ahead. B to A. You have to keep doing work with me. You will be giving me answers, right? B is the origin, 0 to 2 meter is the length. What is the equation for moment? Anyone? Let me give you it. Minus P 2 plus 2. Now x is here. Please understand. X is here. This is the x. This much is the x. So it has to travel. This point load has to travel 2 plus 2, 4 meter. So it will be 4 plus x. Right. Then negative total UDL. Now you have to consider and take moment of total UDL somewhere here at the half of the length, which is 1 meter. So 10 into 2, that is 20. So first I will write 20 into 1 plus x. Why? Because 2 meters and half of 2 meters is 1 meter, and then you have to go ahead x times more. So 1 plus x, which is very obvious. So I'll complete this over here as an equation, right? This is a table. And now if I take partial derivative, again it is 4 plus x. So now friends, we are almost done with all our necessary arrangements. So let's go for delta D. It's going to be long today, long equation today. So 1 upon EI as a constant I'm taking out of the every step. So every time we don't need to write it. 0 to 2 meters. We'll keep simplifying also. Px square dx plus, let's say 0 to 2 Now let's combine this together, like this p into 2 plus x plus 10x square by 2 into 2 plus x dx, and then of course finally plus 0 to 2 meters. We'll simplify it with the signs and all. So p into 4 plus x minus 20 into 1 plus x into 4 plus x dx. Well, I do have the answer, but you just first of all try to simplify this. We'll still keep it outside the overall equation. So, and we'll not integrate it yet because we need to simplify these terms. 0 to 2 meters px square dx, right, plus 0 to 2 meters. Now let's simplify this, and we'll not put p equals to 0 at this moment. Let's try to simplify further. P into, let's say, 2 plus x square plus 10x square by 2 into 2 plus x. Okay. So now this completes, and plus third one 0 to 2, will multiply this again, 4 plus x square minus 20 into 1 plus x into 4 plus x dx. Please make sure that we have not make any mistake. This should be positive. Okay, this will be positive. Now it's a right time, it's a good time to put p equals to 0 so that we can avoid our some of the terms. So let me put it like this. Let's use now, sorry, now p equals to 0. Okay, so now let's go for it. Which are the terms that we are going to cancel? This will get cancelled completely. This term will also get completely cancelled. So we'll retain this one. This term will retain. Again, it's going to be completely get cancelled. So this term we are going to retain. So our equation in a way becomes shorter, right? So it is easy to handle actually. So that's why I have written it like this. So 0 to 2 meters. Uh, First is 10 x square by 2 into 2 plus x plus 20 into 1 plus x 4 plus x dx. So that has now reasonably small for us to handle. So let us expand it completely and then we will take integration. 0 to 2 meters. Uh, 2 and 2 gets cancelled when it multiplied. So 10 x square plus 10x cube upon 2 plus, first we'll multiply, we'll keep 20 still outside this, 1 into 4 that is 4, 1 into x that is x, plus x into 4 that is 4x plus x square, right? And then later on you can multiply 20 simply with this term. So I don't want to lose the charm of writing everything on a same slide, so I'm using this non-ruled space here, so please bear with me for that. 1 upon ei, right? So let's now integrate. It's almost ready for us, so we'll integrate it. And since the length is also constant, so there is no problem at all, so we can go as it is, like 10 x cube upon 3 0 to 2 plus 10 x raised to 4 upon 8 0 to 2 plus, now we can go separately also if you wish. 20 into 4, that is 80. So 80x, again 0 to 2, plus let's say 20x square by 2, 0 to 2, plus 80x square by 2, 0 to 2, plus 20x cube upon 3, and that is also 0 to 2. I think that completes our entire equation. So now I'm giving you 1.5 minutes, 2 minutes. Please give me the final answers. Just replace x with 2 and carry out the calculation, and give me the final answer in terms of total numerator, and later on we'll find out the overall value. So first you give me this value, total of this calculation. So you take your 1-2 minutes and give me the final answer. Once you are done, raise your hand please, so that I can unmute yourself and you can share it with others. But don't hurry up, but take your time, however, and give me the right answer. And we'll tally this with at least one other student also. All right, Darsha, you can unmute yourself.
Sir, I am getting 4.60 mm.
Okay, come again. What is the value?
4.60 mm. Here it is
Oh,
460.
you have directly given me the final answer.
Yes, sir.
Okay, 4.60
60.
mm. I was waiting for numerator. Anyways, you have converted everything into the EI and all this, right? So that is okay.
Sir,
Yes.
it was 460 by EI.
Okay. 460 by EI, and then you eventually use the kilonewton into meter cube, and then you converted everything together. So you have reached the answer. Okay, fine, Darsha. That's okay. So anyone else who has received this answer, just to have a confirmation. Prashant. Yes, Prashant.
Yes, sir. 460 upon EI.
Very good, excellent. So you guys did a very good job, and this inspires me to continue to doing work like this. So thank you. Okay, Prashant.
Thank you, sir.
Yeah. So we'll carry on with the another quantity with this kind of calculation, and I hope it also inspires others to keep working like this. So what is our next target is the slope, right? As you can see here, it's a slope. So we don't need earlier equations, because our all the equations will be new together altogether. So I'm putting it here again. Let's quickly, you can, if you are comfortable, you can go ahead of me, no problem at all. So I will be using this 2 meters over here, right? And now this is 10. Okay, all distances are just for a confirmation, 2 meters, 2 meters, and 2 meters. We have uh, moment, and that is 0, because we don't have any externally applied moment. So A, B, C, and D. Now we are in search of theta D. So always have this quantity in front of you, so that you can accordingly write down your equations properly. So first thing is DC, origin is D, right? 0 to 2 meters. Okay. The equation is very simple, so I'll go with it alone. Minus m, and eventually it becomes minus 1. This is nothing but del mx upon del m. Okay. So C to B now. And C is the origin. 0 to 2 meter is the length. Minus m remains as it is, minus 10x square by 2. This is minus 1. And finally, B to A, origin is B, 0 to 2 meters. Now m goes as it is, minus m. Then you have a 10 into 2 as a total force, 1 plus x as a moment, right? And then we have minus 1. So I think it's very easy, quite easy job for you. So let's put it together. Uh, Theta d equals to, take 1 upon ei constant over here, and then let's join everything together. 0 to 2 meters, that is m dx, right, plus 0 to 2 meters, let's say m plus 10x square by 2, that is dx, plus 0 to 2 meters, finally m plus 20 into 1 plus x, right, and dx. So now we are ready to assign m equals to 0, and we will be able to reduce our equation like anything. So let's see what happens. Still will not integrate it. This will get cancelled. This also will get cancelled, and this is also will get cancelled. So 0 to 2 meters, 10x square by 2 dx, plus 0 to 2 meters, 21 plus x dx. So it's a short and sweet equation. So we'll quickly be able to integrate it now. So I'll be writing it here. Theta d equals to 1 upon ei, and let's say this is 10 to the power cube of x upon 6, right? And its limit is 0.2 plus, here again 21 plus x whole square divided by 2, and its limit is 0.2, right? So it's like this. So we'll expand this equation also. So let's say it goes like this: ei 10 2 cube upon 6 plus 20 into 1 plus 2x plus x square, right, upon 2, where you can replace the x at a parallel stage also, or later on you can use it, not an issue. But it is always good to do all the operations at one hand only. So ei 10 to the power 2, will keep it as it is just for a sake of continuity, right? 1 plus let's say 2 into 2 plus, here we'll put this 2 in the denominator, and 2 squares, right? So now you people have to answer again. Now everything is simplified, so you can give me the final answer of theta d in terms of everything, in terms of considering ei and all. Give me the final answer in radians. Okay. And once you are done, just let me know. Okay, Prashant. Yes, Prashant. I have unmuted you. You can unmute yourself also.
Sir, 103.33 upon EI.
No. Give me the direct answer. Delta theta d in radians directly.
Okay, sir.
Try it. Try it. So it will be very small quantity actually. 0 points or let us say 1.0 into 10 raised to power minus 4 at least. I guess it's very small quantity. Very small quantity. Yes, Prashant.
Sir, is 0.0010.
0.0010.
10.
So what's happening over there? Any other answer? Anyone else? Yes, Darsha.
Yes, sir. It is correct. 0.0010.
Very good, excellent. Now we'll go ahead. So we have learned how to calculate deflections and slope at various positions. So I want you to keep this in secure position. We'll be coming back to this slide. Now I want you to calculate slope at C. Let's go for it because we can compare it easily, right? Let's go for it. In a same beam, it is already there in our question. But first you go for slope at point C, right? So this is 2 meter, this is 2 meter again, this is 2 meter itself, this is 10. So what we should do now, because we want slope at point C, A, B, C and D. So what we should do, we have to apply. If you want, what is your required quantity? Required quantity is theta C. So obviously you will have to apply moment at C, which is fictitious. So let's see how to write the equation. Theta C equals to, sorry, it's not just like that. We have to first of all develop the equation. D to C, what is the origin? Origin is D. Never ignore these things, right? Because it will give you tremendous clarity. Mx 0, del mx upon del m is also 0. Then C to B, C becomes the origin, 0 to 2 meter is the length. Now minus m minus 10x square by 2 minus 1, and finally B to A, right? B becomes the origin, 0 to 2 meters minus m minus 20 into 1 plus x and then minus 1. So guys, there is no need to work upon this. What I wanted to tell you that you will be learning a new behavior is, you will, with your surprise, the answer will be same, right? But try it first. Try it first. Theta c equals to 1 upon ei, like 0 to 2 meters. Everything is 0, so there is no need to do it. 0 to 2 meters. Let's say m minus 10x square by 2 dx and plus 0 to 2 m plus, sorry, not minus, plus m plus 20 into 1 plus x dx. Okay, so I think you can focus here, and now we can replace m with 0 because that doesn't exist at all. So our theta c becomes 1 upon ei. Let's ignore this one, let's ignore this one. So it is 0 to 2 10x square by 2 dx plus 0 to 2 20 into 1 plus x dx. Okay, so we'll come here again for next calculation. Theta c 1 upon ei, right? I hope you are doing with me. uh, let's integrate it now. 10 cube upon 6, right? The limit will be 0 to 2 plus here 20 1 plus x square by 2, right? The limit will be 0 to 2. We can expand it. So theta c again equals to 1 upon ei, right? Let's keep it as it is for a while until we expand this. So now can you compare this value with one of your previous equation here? Isn't it same? Surprising, right? See, it is same for theta d, and now for theta c it is same. So that's what I wanted to tell you, that now you can understand that unless there is a variation in the loading beyond a point, the slope in the cantilever remains constant. That is the outcome of this numerical. That is the important point you have to learn about the behavior of the cantilever. However, the deflection will be different. You will find the deflection at point C now, which is next target. Deflection will be less, however, but there is no variation in slope. Slope will be the same value. You can find it numerically now very easily as in case earlier. So I am even not writing anything here, but you just tell me once you confirm the answer. You can confirm your answer. Yes, Darsha.
Yes, sir, it is same 0.001 radian.
Yes, it is 0.001 radian. So now we have confirmed this behavior. Okay, thank you, Darsha. For this, we can now draw one behavioral, sketch just for your additional discussion. I'm just discussing it as it is. Suppose you have this beam, and if I have force over here, till here only. So this region will not see any change in theta value. Whatever theta value you will find here, it will be here only. Okay, so that means there is a length which is not loaded, so there is definitely no variation in any of the deformation. So it is just like this. So this slope will be constant. So that's what you have to understand. Now quickly let's move to the next target, that is deflection. Come on guys, we'll do it. That is what is the last calculation I will say for this class. uh, this is the UDL, this is A, this is B, C and D. This is 10 we know, and we all know that we require a point load where we want deflection. So this P is 0. Okay, so let's go for it, and don't make a mistake by assuming that the deflection will also be same. No, it's not like that. Please be careful. So this is 2 meter, 2 meters and 2 meters. All right, so this is deflection at C, and for that we need D to C, first segment. D is the origin, 0 to 2 meters, no load, no moment, and no moment, then no other value, right? So C to B, C is the origin. You can do parallel with me, or you can go ahead of me also, no problem. 0 to 2 meters, so that you can give me the final answer earlier than this calculation. Minus p into x minus 20 x square by 2. This is minus x. Okay. And then finally b to a, right? B is the origin, 0 to 2 meters. Then we can have minus p into 2 plus x minus 20. Sorry, here it will not be 10. It will be, it's not 20, it is 10. 10x square by 2. Here it will be 20 into 1 plus x. And here it is 2 plus x. So now I'll sit back, relax, and you just give me the answer. Delta C is given as, let me give you the primary equation, but all of you, it seems that only two guys are working here, so others are also encouraged and inspired to give me the answers. Let's have some voice over, change of voice. 0 to 2, right? First is, everything is 0, so there is no point of doing anything over there. 0 to 2, so that is now px plus 10x square by 2 into x dx plus 0 to 2 uh, p into 2 plus x plus 20 1 plus x into 2 plus x dx. So now you guys have to work on this. I will be relaxing, I will be sitting back, assuming that you are comfortable at this calculation, but you have to give me the final answer of delta C, and that we will compare with earlier value of delta D, right? So you just tell me, take your time, 2 3 minutes, not an issue, and you give me the final answer. I'll be waiting for your answer, any one of you. And then we'll combine UDL with the applied moment. So you can raise your hands when you are done. Yes, Darsha.
Sir, I am getting 2.73 mm.
Let me write here 2.73 mm. And what was delta D? What was the value of delta D, Darsha? earlier we have calculated, right? Somewhere here. 4.06, right? So 4.06 mm. So you can now visualize that the behavior will be like this. It will be like this, and this is 2.73 mm. This is 4.06 mm. And obviously, if you calculate deflection here, it will be lesser than that. So suppose let's say it's around 1 or something, 1.5 something, right? So by this we can confirm the answers also, that they are right in a nature also, and it also explains the behavior of this cantilever. So this is the point you have to learn, friends, that how you will use the data that you are calculating. It's not all about figures always. It's more than the figures. You have to use the information that you are obtaining from the calculations, how to relate it with the behavior, and you have to keep confirming this behavior also. Like here, once you have confirmed now that these values are gradually decreasing from free end to fixed end, so there will be a point where eventually it will be zero, right? So now this values are themselves telling you that there is a particular specific pattern of the deformation of this beam, and you can understand that better way with the help of numerical answers. But similarly, you have understood one more important behavior is the change of the slope does not take place if you don't have any force in a particular region of the cantilevers. For example, again, I will take it like if I have a structure like this, right, and I have one force only here. So definitely this deflection will be different, right? This deflection will also be different, but this tangent, the slope will be constant only, right? So you will have a slope because we don't have any load variation. Okay. So that is the speciality, that is the significant or salient feature of the cantilever itself. When you don't have load variation, it will show the continuous rotation effect. Right. So it's like that. So now if you wish, you can carry on with the calculation of this numerical also, or I will still keep it aside because the only difference is the moment, right? So here you have to include this moment this time into the calculation for the equation and start calculating these values, right? So today I'd like to pause the discussion over here because of the calculation part, which is very similar to the just now we have discussed over here. The only thing is you have some additional moment over here. Now let me tell you how to do it, how you will cope up with that condition. Let me show you quickly. uh, let's say we have a beam like this, and we have UDA. Okay, and now we have a moment this time, which is m equals to, let's say, 10 kilonewton into meter, and this UDL is also, let us say, 10 kilonewton per running meter. This is 2 meters, this is 2 meters, this is 2 meters. Just to demonstrate how you will create equation A, B, C and D, I'm just showing you. Let us say, for example, we are interested in deflection at D, right? Assume EI is constant, and you can change this UDL value to the original value of 25 kilonewton. Here I am just showing you the equation only. So first part is D to C. What is the origin? D is the origin. What is the length? 0 to 2 meters. Then what is MX? What you have to do next now? Anyone? What you have to do now? What is needed in this case? Anyone from the class? What is missing over here? Yes, that's right.
Sir, we have to apply the fictitious point load at D.
Point at point D.
Yes, sir.
Okay, great. So that was intentionally I did not applied and I was waiting for that moment that somebody will raise that point, right? So this is what you have to introduce over here, and we'll do it uh, minus px minus 10, and this is x. Okay. Now C to B. Let's go ahead. C is the origin, 0 to 2 is the length. Now let's take it further. P into 2 plus x minus 10x square by 2, right, minus 10, that is the moment, right, and here it will be 2 plus x. And finally B to A, origin is B, length is 0 to 2. The equation will be P into 4, sorry, P into 4 plus x minus 10 into 2, that is total force, into 1 plus x minus m, right, and here it would be 4 plus x. That's all. So this completes your equation, and I'm sure that if you use this as the way in which we have used, instead of m, why not to use 10, because it is not constant, it is value actually, right? So guys, I think now we are more than comfortable to carry out the calculations. I just wanted to demonstrate you. Later on you can put p equals to 0, so you'll be getting your desired answers in this case. Darsha has a question, raised hand. Yes, Darsha.
Sir, I calculated that sum where the UDL is 25 kN per meter.
Oh, amazing. Very good. So can you share your answers?
Yes,
Let
sir.
me let me write them here itself. So all of you, other students, can get a reference of her answer, and you can also compare your answers over here. Yes, quickly. Theta D,
Sir, sir, it is 0.003 radian
0.003 radian. Very good.
and 11.5 mm
11.5 mm. Excellent. Delta C,
and 7.47 mm
7.47 mm, and
and 0.0032 radian.
yes, so that confirms the behavior as I explained. So very good work, Darsha. I appreciate your efforts and sincerity. So thank you again for sharing these answers. And see, I request everyone to record these answers for their comparative work. If you have already solved this numerical, you can compare your answers. Otherwise, you can note down these answers. They are correct, perfect, and you can see that theta D and theta B are again matching, so they are not changing their slope effectively unless you have any tremendous change in the load like this, right? If there would have been load like this, then this would have not been the same answer, right? So, guys, I think now it is from this result, I'm more than happy that you people are working hard and also practicing very good. You should also keep practicing. Tomorrow, I'll be taking one more lecture. So, we'll be meeting tomorrow as well, probably at 9 o'clock. and we'll be also carrying out some numericals, probably with the first principle of the energy, second principle of the energy. I would like to begin because most of the no, but yet we have to consider the simply supported beam, right? So tomorrow probably we'll take energy principle number one applied for the simply supported beam. It is also amazing exercise. So keep doing practice like this. I'm very happy with the feedback from your class, and please keep doing these things again. Right. So I'll take your leave now. I'll pause the discussion, and we'll meet tomorrow. Albert, quickly you can tell me what you want to tell.
Yes, sir, I have a question.
Yes, you have the same answer.
No, I have a question.
Sorry, I'm you're, I'm not getting your voice clearly.
I have a question I'm asking.
Ah, you have a question. Okay, please tell me.
On the original diagram, we had a moment of 10 kilonewtons at point D.
Okay.
When I look for deflection at point D, why do we ignore that moment?
No, no, we have considered it here now. This is what the moment is. This is all moment only, dear.
I mean the previous one, not this one.
Previous one. Here. Uh, or even here.
On deflection at D. There.
Deflection of D.
At
Deflect.
D, we had a moment of 10. For you putting moment equal to 0.
No, no, we didn't have any moment here. This was the only case where I just wanted to explain you this without external moment. It was not at all there. See, I just wanted to separate this numerical first as only UDL, and that's then once you understand how to work with UDL, like which is non-uniform, then only I introduce the real question. So this is the real question, and this was the another practice numerical that we considered without moment, right? So I just wanted to you to explain separately, because the question which I shared with you as a homework, which was consisting both forces, right? So what I did today, first I explained you how to solve this problem, and then I clubbed together with UDL as well as moment. So in the original first problem, in the original question, there is no moment at all.
All right, I get it.
Yeah, thank you, thank you. And it's good that you have asked this question. So I'm appreciating your involvement also. So thank you all for joining, and we'll meet tomorrow morning again with some exciting new concept on how to apply these things in the simply supported beam. So thank you all. I'm stopping here, taking your leave now. Have a happy day ahead. Thank you all.